Good morning, everyone. Am I audible? Hello. Yeah, okay. Is this slide visible?
Oh, yes.
So, hello, everyone. This is Srish VP and here's my mate Ayush. Today, we will be conducting a workshop named Equations of Destruction, Mathematics of Ballistics, Trajectories, and Weapon Accuracy. So, let me begin this session by asking you something. Have you ever watched a cricket shot and had predicted correctly where the ball would go? Like, whether will it hit the boundary or would be caught by a fielder? Can anyone answer this?
Yes.
Okay. I hope everyone had at least predicted that correctly at least once. So, what you are doing at that moment is actually physics, trying to guess the trajectory followed by the ball. So, moreover, it is mathematics in action. So, today we are going to take a simple idea of throwing a ball and extend it to something as complex as a guided missile. So, in modern systems, nothing is random. Every movement, every trajectory, and every impact is governed by mathematics and precisely calculated. So we will be studying how the real world behave and how systems use mathematics to predict, control, and optimize motion. You will be understanding how modern systems think, how they calculate paths, adjust mid-flight, and achieve accuracy. So with that, let's begin our journey into the mathematics that governs motion. So this slide shows the roadmap for today's session. First, we will start with projectile motion, where we build the fundamental understanding of how objects move under gravity. And then we move to ballistic trajectories, where we extend those ideas into real world conditions. Next, we will explore modern ballistic systems, where physics meets technology, involving how sensors, computation, control systems work together. And after that, we'll be going into optimization and targeting systems, where we understand how systems choose the best possible trajectory and minimize error using advanced mathematical techniques. Finally, we'll be looking into accuracy and impact, which focuses on how all these concepts come together to ensure precision in real world applications. So, in this workshop, we will take you from basic physics to advanced real world systems step by step. So, now let's begin with most fundamental question. What is a projectile? A projectile is any object that is launched into the air and then moves only under the influence of gravity. Let's understand this through some examples. First, you take a ball that is thrown into the air. When you throw a ball at an angle, it moves forward and goes up, reaches a peak, and comes down. This is the most basic example of a projectile motion. Now, consider a bullet. At first glance, it might seem completely different because it moves extremely fast and almost in a straight line when compared to a thrown ball. But in reality, it is still a projectile. The only difference is that the speed of the ball and the speed of the bullet. It is because of the high velocity of the bullet, we do not see it falling while moving forward. But the gravity is still acting on it. It is still a projectile motion. Now, let's take a more advanced example, a missile. You might think a missile is not a projectile, but you would be partially correct. But while the engine is active, it is not a projectile because the engine gives a thrust to it or some external force in order to accelerate it. But the moment the engine stops, it becomes a projectile. From that point onwards, its motion is purely governed by gravity and other external forces like air resistance, wind, and rotation of the Earth, about which we will be studying later. So, because the real world motion is actually very complex, so what do we do is create an ideal model. This ideal model is based on many assumptions. Now, let's look into the assumptions of the ideal projectile motion one by one. First one is that the air resistance, which is also called drag. It slows down objects, but in our ideal model, we ignore it completely, which means that the object never loses speed due to air. It keeps moving as if it were in a motion. Next is wind. In the real world, wind can push objects sideways, but here we assume no wind at all, so there is no sideways deviation. The motion stays in only one plane. Only. The next we come to spin and the Magnus effect. If an object is spinning, it can curve in the air. But here we ignore this completely, so there will be no unexpected motion. Next is thrust forces. As we have discussed earlier, this is very important for rockets and missiles. In real systems, engines provide continuous force, but in projectile motion, we assume that once the object is launched, there is no more external force or any propulsion to it. So the motion is just purely influenced under gravity. Next is the Earth's rotation, which is also known as the Coriolis effect. The Earth's rotation can slightly shift the path of moving objects, especially over long distances. But in our simplified model, we ignore this completely. The next is that variation in gravity. In reality, gravity is not perfectly constant everywhere. But here, we assume the gravity to be a constant of 9.81 meter per second square. So we make these assumptions in order to build a clean and simple mathematical foundation. But very soon we'll be bringing all these factors and all the complexity of the real world together. Now, Adhikappa, we will see the key variables in projectile motions. U denotes the initial velocity, theta denotes the angles of projection, T denotes time, and G denotes gravitational constant, which is 9.81 meter per second square, and X denotes horizontal distance, and Y denotes vertical height of a projectile at any point. So, when you launch a projectile at an angle, it might look like one single curved motion, but mathematically, it is actually two motions happening at the same time. So in this slide, we will be resolving the velocity component of the projectile motion, one in the horizontal direction and one in the vertical direction. And the most surprising part is that these two motions are do not affect each other; they are independent of each other. They're completely independent. First, we look into the horizontal motion separately. In the horizontal direction, there's no force acting in our ideal case, which means there will be no acceleration. No acceleration means the velocity remains constant. So the horizontal velocity is simply the initial velocity multiplied by cos theta. And this value never changes during the motion. So horizontally, the projectile keeps moving forward but at a constant speed. Now we will look into vertical motion. In the vertical direction, there is gravity acting on the projectile. So there is always constant acceleration downwards. The initial vertical velocity is considered to be initial velocity multiplied by sine theta, that is u into sine theta. Now, as the projectile moves upwards, gravity slows it down. At the highest point, the vertical velocity becomes zero. Then, after that point, it starts falling and gravity speeds it up downwards. So, altogether, horizontally, the motion of the projectile is a constant, and vertically, the motion of the projectile is accelerated. And when you combine these two, you get a curved path. Why a curved path? Because it is moving forward at constant speed and while continuously and simultaneously falling down due to the gravity. This combination makes the path curved. So this diagram illustrates what we have discussed before. So let us try to resolve the velocity component of the projectile into horizontal and vertical. First, we'll focus on horizontal component. Here we can see that throughout the entire trajectory, the horizontal component remains the same. That is, the length of the horizontal component is always the same and it always points in the same direction, which means that this tells us this is always constant throughout the motion. But if you see the vertical component, it is the highest when it is at launch, and the component keeps on decreasing as the projectile moves to the highest point. It is because of the gravity acting downwards, and after this point it seems to change its direction. The vertical velocity component changes its direction and starts acting downwards, and it keeps on increasing as the downward gravitational force accelerates it. So now we will discuss about the shape of the trajectory formed by a projectile in motion. Okay. From the diagram only, we already know that this path is curved. But what exactly is this curved path? When we combine the horizontal and vertical equations of motion that we have seen before, see, which is x is equal to u cos theta into t and y is equal to u sin theta into t, which is also equal to half gt square. When we combine these two equations, uh, we get a single equation that describes the entire path. This path turns out to be a parabola. This equation is the equation of a parabolic path traced by a projectile. Y is equal to x into tan theta minus g into x square divided by 2 into u square cos square theta. So, this equation tells us for any horizontal position x, we can calculate the vertical height y. This means that we can, using this simple equation, we can trace the entire part of the projectile. Okay, and most importantly, the presence of the x squared term in the right hand side of the equation is what it makes this equation parabolic. So the path, the couple traced by projectile depends upon the angle, depends upon the initial velocity, and also on gravity. Okay. So let's move on to range. Range is nothing but total horizontal distance covered by a projectile. It is given by the formula r is equal to u square into sine 2 theta divided by g, and it is a maximum. That is, the range is maximum when theta, the projectile angle, is 45 degree. And range is also directly proportional to u square, which means that if you double the speed, the range becomes 4 times its original value. Now we will look on to the maximum height. Maximum height is nothing but the highest point reached by the projectile, which is nothing but this exact point where the velocity of the projectile is 0, the maximum height is achieved. So it is given by the formula h is equal to u square into sine square theta divided by 2g. Okay. Mm. It depends upon the angle, projectile angle theta. If it increases, this value also increases. If it decreases, the maximum height reached by the projectile also decreases. Next, right? Okay. Now let's take everything we have learned so far and scale it up to one of the greatest achievements in human history, the Apollo 11 moon landing. When NASA sent humans to the moon, they didn't just launch a rocket and fly straight there. In fact, it is not possible to do so because space travel doesn't work like driving car in a straight line. Instead, they used a concept that is very similar to what we have just studied, which is nothing but projectile motion, but on a very, very massive scale. Let me explain this in a simple way. Okay, when this spacecraft was launched from Earth, it was given a very precise velocity and direction. Okay, after the initial powered phase, when the engines are no longer continuously accelerating the spacecraft, it starts behaving like a projectile. At that point, the spacecraft is essentially falling towards Earth, but at the same time, it is also moving forward with such high speed that it keeps missing the Earth. It falls downwards, but in a very, very small scale that we do not know, that it is not noticeable. The spacecraft is always falling but never hitting the ground. And this is exactly what an orbit is. An orbit is nothing but a projectile that keeps missing the Earth. So now, as the spacecraft moves farther away from the Earth, something interesting happens. The influence of Earth's gravity decreases, and the Moon's gravity starts influencing the projectile motion of the spacecraft. So now the motion is no longer governed by just one gravitational field; it is influenced by two bodies, Earth and Moon, which means the trajectory will no longer be a simple parabola, but it becomes much more complex. But the idea remains the same. The spacecraft follows a curved path determined by the gravity and its initial velocity. So, in simple terms, going to moon is just a projectile motion, but with changing gravity. So now let's make a real life calculation example. Now consider a scenario where you are a sniper and and the target is 30 meters away from you, and the speed of the bullet that you are going to fire is 30 meters per second. Okay. Now, you may think that. Hello? Hello?
We
Yeah,
can
you're
hear
Audible?
audible.
you. Yup.
Yes. Okay, fine. So, what do you think is that if you fire the bullet, it will travel in a straight line and directly hit the target? But you are completely wrong. Let's find out by doing some calculations. First, let us calculate the time of flight, which is nothing but t is equal to distance by speed. Here, the target is 30 meters away, so the distance will be 30 meters, and the speed is 30 meters per second. So the time of flight will be 1 second. So now we calculate the bullet drop, which is given by the formula y is equal to half gt square, as we have discussed earlier. Which on substituting t is equal to 1 second, we get the value as 4.9 meters. So during a flight of 1 meter, covering a distance of 30 meters, the bullet will drop by 5 meters. Now let us see what happens with the help of a simulation. Okay, so as we have discussed, the target is present here 30 meters away from the person who is holding a gun. Let's assume that this is a gun, and the initial the speed of the bullet when fired from the gun is said to be 30 meters per second. So now the couple it is at a height of 5 meters. So assume here there's a person 5 meters tall is standing here. So let's see what happens when we fire the bullet. So as I've said, the bullet doesn't travel in a straight line. Okay, uh, but it falls as we have calculated. The bullet drop is approximately 5 meters. So here we can see that the height at which it is fired is 5 meters. So then when it hits the target, the altitude of the bullet becomes zero. So the drop is 5 meters as we have calculated. So if a person is standing here, it might not go straightly and hit him at his head, but it falls down. So in order to correctly hit the target where we have intended to, we make small adjustments. Like here, I I make a small adjustment in the angle. I increase it to 5 degree from 0 degree. Now let's see what happens. Now still it is missing the target. So I'm gonna increase it to 10 degrees Celsius. Now let's see what happens. Yeah, now it might be hitting where we actually wanted to. So like this, the real world systems also make some adjustments according to the situation and other external factors, so that it would correctly achieve the objective. Okay, now let's move on to the next slide. So okay, this slide is extremely important because this is where everything we assumed earlier starts breaking down. Let's go back for a moment to what we discussed in slide 4. Yeah. In slide 4, we have made several assumptions to simplify motion. So we assume there is no air resistance, there is no wind, there is no spin, and there is no earth rotation. There is constant gravity. And we said we are imagining a perfect vacuum. Now we are going to what we are going to do is bring reality back in. So one assumption at a time. We will be going to bring back one assumption at a time into the real world, and you will be seeing how each assumption we made earlier directly affects the motion. Yeah. And just a minute, there's a slight internet issue here. The pages are not loading. Okay. Now, now we arrive at a new constant, which is called ballistics. Okay. Ballistics is the science that studies how projectiles move from the moment they are launched to the moment they hit the target. So, projectile motion is a simplified model. Ballistics is the real world application of that model. Now, let's clearly compare the two. Ideal motion versus real ballistics. In ideal motion, the path is a perfect parabola, only gravity acts. Motion is predictable with simple equations. But in real ballistics, the path is distorted, multiple forces act simultaneously, motion becomes complex and dynamics. So the core idea of motion doesn't change, but only the accuracy of prediction becomes much harder. And this is why ballistics is so important because it directly determines accuracy in weapons, effectiveness of defense systems, success of space missions. Now let's think about this practically. If you ignore real world effects, even a small error at the beginning can lead to a huge miss at the end. For example, consider a slight wind or a small drag effect. uh, it can shift the projectile by meters over long distances. So systems cannot rely on simple formulas anymore. They must account for air resistance, wind, spin, Earth's rotation, all at the same time. Now, here's a key shift in thinking. In projectile motion, we try to find exact equations, but in ballistics, we often cannot get a single exact equation. Instead, we use models, approximations, and simulations. So the focus changes from finding one formula to model the system as accurately as possible using models, approximations, and simulations. So there are three phases in ballistic motion. First one is the launch phase. Okay, this is where everything begins. In this phase, an external force acts on the object. For example, in a gun, the expanding gases pushes the bullet. In a rocket, engines provide thrust. In an artillery, explosive force accelerates the shell. Okay, this phase is all about giving the projectile its initial velocity and direction. And this is extremely important because once the projectile leaves this phase, uh, you cannot change its motion easily unless it is a guided system. Guided system is nothing but it is a system which has ability to adjust its flight and adjust its trajectory using some advanced components like GPS tracker, computer systems, and and many other units uh, which help them to do so. So, um, the entire trajectory depends heavily on what happens here. Think of it as like setting the initial conditions in an equation. If the starting values are wrong, everything that follows will also be wrong. Okay. Now let's move to the second phase called free flight phase. Okay, this is the phase where the projectile is no longer powered. There is no thrust. There is no any external force. There is no engine pushing the projectile. So now motion is governed by forces like gravity, air resistance, wind, possibly spin effects. This is where all the complexity we have discussed earlier comes into play, and this phase usually lasts the longer when compared to other phases. So in this phase, the projectile follows a trajectory that is continuously influenced by these forces. For unguided systems, the motion is completely passive, but for guided systems, this is where corrections happen. Like they might have sensors which track position, and computers which compare actual desired path, and control systems which adjust the trajectory mid-flight. So even though it is called free flight, modern systems can still influence the motion here. Now we come to the last phase, which is called impact phase. So the projectile has to reach its targets at the end. So at this point, the motion ends and the energy is transferred. So everybody know that an object while in a motion carries kinetic energy, and this kinetic energy, when the projectile hits the target, will get transformed and transferred, and it gets transformed into some other kind of energy. So depending on the system, this could mean a bullet hitting a surface, or an artillery shell exploding, or a missile reaching its target. Okay. Okay. From a physics perspective, this phase is about energy transfer. Kinetic energy becomes impact energy. Okay. This picture illustrates that real projectile paths are not perfect parabolas, as we have discussed earlier. This is due to several factors like air resistance, wind, rotation of the Earth, also known as Coriolis effect. And this is just to demonstrate that the motion in real life is more complex than ideal equations. Now let's move on to next slide. Okay. Now we move into one of the most important parts of this workshop, modern ballistic systems. Up until now, we have understood two things. First, the ideal motion, which is simple and clean. Second, the real world motion, which is complex and affected by many forces. Now the question is, how do modern systems handle this complexity? Let us see that. Modern systems don't work by using one direct formula. They simulate motion step by step instead of trying to calculate the entire motion at once. So, in order to do so, we divide time into very small intervals called a time step. Okay, it's usually very small. Like we take a time interval of like 0.0001 seconds. Okay, now at each very small time step, the system performs four key operations. The first operation is that they compute forces. They calculate all the forces acting on the projectile. So at that instant, we know the total force acting on the object. The second operation is that using Newton's second law, which you all know that force is equal to mass into acceleration, it tries to update its acceleration. So from acceleration, we actually get how the velocity will be changing. So once we know that, we try to update the velocity. We try to update the velocity by knowing how much it's gonna change in that small time interval, and add the effect of acceleration over that small time step. Now, finally, we update the position. We take the current position and move it forward based on the velocity that we have updated before. So by doing so, we get the new position. So this process is repeated again and again, like thousands of times per second. We have discussed earlier. This process will be repeated again and again for each time step. That is very small, like 0.001 seconds. So per second, approximately, this all these four operations will be repeated like thousands of times. Okay. So instead of jumping directly to the final answer, the system builds the trajectory point by point. Now here's something important. The smaller the time step, the more accurate the simulations. Okay. Um, Now we come to drag force. Drag is nothing but a force that opposes motion when an object moves through the air. So whenever a projectile is moving, air is pushing against it in the opposite direction, and this force is not constant. It depends on multiple factors. Okay. So the mathematical expression for drag force is Fd is equal to half into Cd into rho into A into velocity square, V square. Cd represents the drag coefficients. It depends upon the shape of the projectile, and rho. Rho is the air density, and A is the cross-sectional area of the projectile, and V is the velocity of the projectile squared. So from this equation, we can tell that the drag depends on the square of velocity, which means if the velocity doubles, the drag becomes 4 times larger than its original value. So what we the inference from this is that at high speeds, drag becomes extremely significant, and this is why fast-moving projectiles lose speed quickly. Now we'll see in which direction the drag acts. Drag is always opposite to the direction of motion. So if the projectile is moving forward and upward, the drag will be backward and downward, which means it will affect both horizontal motion and vertical motion. So drag is not just slowing the speed of a projectile; it is also constantly changing its trajectory. Now we move on to ballistic coefficient. This is nothing but it tells how well a projectile can resist air resistance. Okay. So higher the value of BC, the lesser will be the drag. Higher the value of BC, the longer will be the range. Lower the value of BC, more will be the drag, and the shorter will be the range. So projectile with high BC maintains speed longer, travels farther, and it is very stable. Why do we use this value BC? In real systems, we don't always calculate drag from scratch by using this formula. Half FD is equal to half into CD into rho into A into V square. We don't always use this formula to calculate drag. Instead, we use BC values that are already measured and tabulated. This makes calculations much faster and more practical. This is why we use a BC over using this formula in order to save some time. Now, let's move on to the next slide. Okay. Till now, we have been asking what is the value. Now we change our approach and ask how is the value changing. And this is exactly what a differential equation does. As everybody know, a differential equation describes the rate of change of a quantity. This concept comes into play because simple equations are not enough for real world systems because the real motion is dynamic. Everything is changing continuously. So let's try to understand this through an analogy. Imagine you are driving a car. If the road is perfectly straight and there is no obstacle blocking and the traffic is very less, there are no cars that go ahead of you, you can just say that the distance covered by the car will be equal to speed into time. This is just a simple formula, but in reality this doesn't work because um, uh, there will be lots of cars moving ahead of you. The roads will not be a perfect straight line. It would have curves and bends. There will be speed breakers, so you have to accelerate, brake, and then again accelerate. So the speed of your car will be constantly changing. Here you cannot directly say that the distance covered by the car will be just equal to speed into time. So instead, you have to track your motion moment by moment. At every second, your speed changes slightly and your position updates accordingly. This is exactly what differential equations do. They don't directly tell you the final answer, they just tell you how things are changing at every moment. So instead of jumping to the result, we follow the motion step by step. So this is why we need differential equations in ballistics. Okay. Now that we have understood differential equations, we move to another important factor that affects the motion, which is wind. So, up until now, most of our discussion has been in only two dimensions, forward and vertical. Okay, but the moment we introduce wind, the problem becomes three-dimensional. Without wind, which we consider to be the ideal case, there will be no sideways force acting on the projectile. The projectile stays in only one plane, and the motion is simple and it is very easily predictable. But the moment we introduce wind, the projectile experiences a force sideways. So now, in addition to forward motion and up down motion, that is vertical motion, we also have sideways motion, which means we now need a new axis. X for horizontal motion, Z for vertical motion, and Y for sideways motion, which is caused due to the wind. So the trajectory is no longer a simple curve in a plane; it becomes a full 3D path. There are three types of wind effects. Crosswind. This is just the wind coming from the side. It directly pushes the projectile left or right. It causes the sideways deviation. Okay. And next type is that the headwind. This is the wind coming opposite to the direction of motion. What it does is that it slows down the projectile. As a result, the range of the projectile decreases. The time of flight increases. The last type is that tailwind. The tailwind is nothing but the wind in the same direction as the motion. It helps the projectile move forward. As a result, the range of the projectile increases and the air resistance is slightly reduced. So, let us now discuss how real systems handle the wind factor step by step. Okay. The first step, they measure wind. Systems collect wind data using sensors, weather inputs, and observations. Next, they compute relative velocity, which is nothing but projectile velocity minus the wind velocity. This gives the effective velocity using drag calculations. So now, as we have introduced wind, the motion of the motion of the projectile will be in all directions. That is three dimensional. So the air resistance also becomes three dimensions. It doesn't only act opposite to the direction of the motion; it also acts on the sideways. And then the next step is that they update simulation. Now all these are calculated and fed as input to the system. So this is fed into the simulation loop. So at each time step, force are updated, velocity updated, and position is updated as we have seen before. And this continues throughout the flight. Next slide is that. Okay. Now let's see why is it difficult to incorporate the factor win in real systems. Let's say consider a real sniper example. Consider long distance shot. Let's say that's a crosswind of just 5 meters per second. That might not sound like very much value, but over long distances, this can shift the bullet by meters away from the target. So even if your calculations are perfect, a small error in wind estimation can lead to a complete miss. So wind is considered to be one of the biggest challenges in ballistic accuracy. It is very difficult because it changes over time. It is not constant. It changes over time, over distance, and also with altitude. The wind near the ground can be completely different from the wind higher up in some other altitude. So the projectile doesn't experience just one wind; it travels through multiple wind conditions. And on top of everything, it is very unpredictable. Wind can come in gusts, it can suddenly change direction, and can also vary in strength, which makes it extremely difficult to predict precisely. So now modern systems try to handle this using something called layered wind modeling. This divides the atmosphere into layers. Each layer has different wind speed and different wind direction. So as the projectile travels, it experiences different conditions at different heights. The layered wind modeling exactly observes everything and calculates everything and makes continuous adjustments accordingly. And this way, modern systems continuously update calculations and adjust predictions in real time. In guided systems, this can lead to mid-flight corrections. Okay, now that we have understood wind, let's move to the another large-scale effect that influences motion, which is nothing but the rotation of the Earth, also known as the Coriolis effect. What is this Coriolis effect? It is nothing but just the apparent deflection of moving objects caused due to the rotation of Earth. The key idea behind this is while the projectile is in the air, the Earth beneath it is also moving. So, from our point of view on Earth, the projectile is expected to shift its position. Here, what we have to understand is that the projectile is not changing its direction on its own, but the ground beneath it is moving. So the direction of the deflection depends on where you are on Earth. In the northern hemisphere, the deflection is to the right, and in the southern hemisphere, the deflection is to the left. And also, we need to understand that different parts of the Earth move at different speeds. Near the equator, the becomes okay. Modern systems handle it step by step. First, it determines the location. It determines where you are on Earth exactly. So first system calculates the latitude. Okay. Then it computes the rotation effect. They calculate how Earth's rotation will affect the projectile's path. This includes direction of deflection and also the magnitude of deviation. And then it finally applies the correction, adjusts the aim. So instead of aiming directly at the target, it aims slightly offset to compensate for the effect. Like we have seen in our simulation, in order to uh, get the desired outcome, I had to adjust the angle at which the bullet was shot. So like that, it will be making some corrections in order to achieve the objective. Okay. Now, let's see a real life example of a artillery shell. M982 Excalibur. It is a precision guided artillery shell, and but unlike traditional shells, it is one is not just fired and forgotten. It actually guides itself during flight. Let's understand how it works step by step. So after launch, the shell is given initial velocity and spin for stability. Then during flight, GPS tracks its position, IMU tracks motion and orientation. Now the onboard computer does something very important. It compares where the shell is and where it should be. If there is any difference, the system makes corrections. And how does it correct? It uses very small fins. Okay, fins are nothing but they are just equipments which are just airflow and slightly change the trajectory of the projectile midway through the flight. So instead of following a fixed path, the shell continuously adjusts itself to hit the target accurately. So now let us look into the components of these artillery shell one by one and what role do they play. First, we will look into the nose section of the artillery shell. This contains the fuse, which controls a detonation, and also it contains guidance electronics and also a GPS receiver. And this is the path which decides where the shell is and where it needs to go and when it needs to explode. The next part is that the GPS receiver. It receives signal from satellites and calculates the exact position of the cell. This gives accuracy up to a few meters. The next component is the inertial measurement unit. Okay, this contains accelerometers and gyroscopes. Their job is to track motion. Even if the GPS signal is weak or it got lost, the IME continues estimating acceleration and orientation. So it acts as a backup and stabilizer. So next thing is that the control actuators and canards, which is nothing but the fins we have discussed before. They are small movable fins near the front. They are responsible for trajectory correction. By slightly changing airflow, they generate small forces that adjusts the path of the projectile. And we will now look into its aerodynamic body. Its purpose is to reduce drag, maintain stability, and ensure very smooth flight. This directly improves range and accuracy, very efficient. The next part is that warhead. It is the part which contains the explosive material and delivers the final impact. So while everything else ensures accuracy, this part ensures effectiveness. Now we move to the base section, which is responsible for spin and stability. When the shell is fired, it spins due to the rifled barrel. This spin provides gyroscopic stability. It prevents the shell from tumbling and keeps the trajectory predictable. And finally, the power supply. Every system needs power. Usually, here a thermal battery is used, which is activated after launch. This powers up the GPS, computer, and control systems. All these components work together to turn a simple projectile into a smart guided system. So a modern ballistic system is not just physics; it is the physics with sensors plus computation plus control, and this is what makes high accuracy possible. Next, we come to optimization. Okay, optimization is nothing but finding out of all possible trajectories, finding which one is the best. Okay. Until now, we have learned only to model motion, how they would account for forces, and how systems simulate trajectories. Now we will see how do we optimize those the couple of things. Yeah. Uh, the system must, in order to choose the best option among all possible trajectories, it first collects all necessary information like distance to the target, wind conditions, ballistic coefficient, and also environmental factors. This defines the problem clearly to the system, and then it generates possibilities. Now the system considers different options. For example, different angles of firing, different trajectories. So instead of just one path, now we have many possible paths. So from those taking all those possible paths, and now the system simulates the cover it runs the cover each possible path and see which one the cover is very close enough to hit the target, and it is more the cover efficient. It compares with the target. Now, the cover, it compares the predicted impact point and the actual target point. The cover which normally gives an error. The goal is to reduce this error to a minimum value, to a very minimum value. So finally, the system chooses the option with the very minimum value. Next slide. Now, this slide shows you how to reduce this error that we have discussed before to a very minimum value. So error is nothing but simply the difference between the where the projectile actually lands and where the target is. So mathematically, error is equal to predicted position minus target position. Our goal is to reduce this error to a value as minimum as possible. Okay. So in order to do so, we use optimization methods in real systems. Uh, there are like 4 to 5 optimization methods, but we are going to look into only one, that is MPZ, which is very importantly used in many real life systems now. We are going to look at that in detail, and before that, we will try to discuss 2 to 3 optimization methods. That's the outline of. Okay, first one is that iterative numerical optimization. This is used in artillery fire control and sniper ballistic solvers. The main idea is that instead of solving directly, systems gives initial parameters like angle and velocity, and then they simulate trajectory, compute error, and then adjust parameters. And this 4 processes are repeated again and again. The second one is that gradient-based optimization, which is also known as continuous optimization. This is used in advanced artillery systems and missile trajectory shaping. The main idea behind this is that they move parameters in the direction that reduces error fastest. And the next one is the optimal control optimization technique, which is mainly used in guided missiles and interceptor systems. The main idea is that instead of choosing one parameter, we optimize the entire trajectory over time. Finally, we are going to see in detail about the model predictive control optimization technique. This is mainly used in modern guided missiles, autonomous targeting systems. The main idea behind this is that they predict future trajectory over a short time horizon, optimize control inputs, and apply only the first step. And these processes are repeated continuously. The objective of the MPs is very simple. We want to find the best control inputs so that the system reaches the target with minimum error and minimum effort. Okay. Mathematically, we express this as minimizing error plus control effort. Okay. Now let's understand what this really means. Minimizing error means staying close to the target. The system tries to minimize the distance between where it is going and where it should go. So the goal here is accuracy. Second, we will see what minimizing error means. Minimizing error means that we don't use excessive control. Okay, for example, we don't overuse fins, or we don't waste much energy trying to control the system where it should go or where it should be in this moment, whatever. So the system aims to be efficient. Here, minimizing error means accuracy, minimizing effort means being efficient. Okay, now the real life world must have many constraints available in it. So the system must operate within those limits. It cannot exceed physical limits, or make unrealistic movements. So all solutions must be practical and safe. Now, now that we have understood the objective of MPZ, now we need to define 2 very important components: the state of the system and the control inputs. Uh, the state vector is nothing but it describes the complete condition of the system at any given time. In this case, we define the state as position and velocity. The variables x, y, z represents the position of the projectile in 3D space, and the components vx, vy, vz represents velocity components i- in the 3D space. Together, this forms the state vector. So the state tells us exactly where the system is and how it is moving at that moment. So if we know the state, we fully understand the system's current condition. Now we will look into control inputs. Oh, so in this system, we have fin angle and thrust adjustment as control inputs given to the projectile. Okay. Fin angle. This controls the direction of motion. By changing the fin angle, we can steer or drive the projectile to whichever position we want. And thrust adjustment. This controls the speed and acceleration. It allows the system to either speed up or either slow down. So the control inputs are the variables we use to influence and change the motion. So putting it all together, now we have the state which tells what the system is doing, and the control which tells how we can change it. This is the very foundation of MPC. Yeah. Now the next slide. System dynamics equation. This equation tells that next state equals a function of current state and control. In simple terms, the future depends on where we are now and what do we do next. Okay. Uh, Okay, here we see the equation x of k plus 1 is equal to f of x of k comma u of k. If here x of k plus 1 represents the next state and x of k represents the current state and u of k represents the control inputs that we give to the current state of the uh, projectile in order to predict future positions. Okay, so this equation tells us how the system evolves over time. Okay. Dynamics is what controls connect inputs to actual motion. Now, using this equation, MPG predicts the future. It calculates a sequence of future states x1, x2, x3, and up to xn. First, it finds x1 using current state and control, then x2 using x1, and then x3 using x1. And this process continues until xn. Now, this is like simulating the motion forward in time. So, MPG, what does MPG do? Is that it looks into the future before making a decision. Now we will see what a cost function is. Okay. Cost function is nothing but it is what the MPG tries to minimize. Okay. The cost function includes two main parts: the distance to the target plus the control effort. So the system tries to stay close to the desired trajectory and avoid excessive control actions. So putting it all together, the process is using dynamics to predict motion, evaluate future paths, and choose the one with minimum cost. So now we come to the constraints. In real world systems, we cannot do anything freely. There are always limits. Control constraints and the state constraints are the two main types of constraints we have to look into. So if we have limits on the control inputs, those are called control constraints. For example, the fin angle cannot exceed a maximum value. So if we write control must remain within a certain range. This ensures that the system does not demand impossible or unrealistic actions. Now we will look into state constraints. Um, okay. This is the limits on the system itself. For example, the projectile cannot exceed certain speeds. It must stay within a safe regions, or it must operate within a particular set boundaries, physical boundaries. So we ensure that the system state remains within an allowed region. The key idea here is that constraints ensures that our solution is not just optimal but also physically possible and safe. So mathematically, we are solving a constrained optimization problem. So finding the best sequence of control inputs that gives minimum error and minimum effort is alone not enough. This must also satisfy system dynamics control limits and also safety constraints. Now we come to the most important and final idea in modern predictive control, the receding horizon principle. Okay. Uh, just a minute. Give me just 1 minute. Uh, Sorry for the inconvenience. Now we may continue the session. So now we come to the most important idea in model predictive control, which is the receding horizon principle. Okay. Now let us see what this principle does. It takes the current state and the system computes an entire sequence of control actions like u0, u1, u2, and all the way up to un minus 1. This is nothing but it is essentially a plan for the future. So this answers the question like what should I do over the next few steps to reach the target optimally, and then it takes among all the values control actions like calculator u0, u1, u2 till un minus 1. It only takes u0 and applies to the system. Why it does only take u0 and apply it to the system, we'll be looking into that question later. So it will be taking only u0 and discarding everything else. So this means that we compute the full plan but we trust only the first step. Okay, and this process is repeated again and again. After applying u0, the system moves forward. Now it measures the new actual state, then it solves the entire optimization problem again from this updated position. So the process becomes measure, predict, and then optimize, and finally act. And this these processes keeps on repeating again and again. So now we will come to that question: why you only apply u0? Now let's consider time k. We complete a plan and apply u0, and we take at time k plus 1. We complete a new plan and apply the new u0. So the horizon keeps shifting forward. Why do we do this? Because the real world is uncertain. Wind changes, sensors have noise, models are not perfect, so predictions made earlier may no longer be accurate and may no longer be the same um, after some time. So we don't follow a fixed plan, we continuously update the plan based on reality. To understand this, let's see an analogy. Think of driving a car in a fog. Okay, you just don't plan the entire journey in advance. You just look what's in front of you for a short distance. If it is clear, you take the next step, just the next step, not the entire, you will not proceed to the end of the road, just a small step, and then again you see whether the road is clear, and then you make the next step. This is what happens here also. So this is all about mpg, and from here onwards I should be taking over this session. So,
Guys, am I audible? Shirish, am I audible?
hello.
Yes, you are.
Okay. One second. So, thank you, Shirish. Before starting my half of the section, I would like to answer the question. I would like to try to answer the question why humanity is going above and beyond to make weapons more advanced with the help of a line that says if you hold a gun and I hold a gun, we can talk about law. If you hold a knife and I hold a knife, we can talk about rules. If you come empty handed and I come empty handed, we can talk about reason. But if you have a gun and I only have a knife, then the truth lies in your hands. If you have a gun and I have nothing, what you hold isn't just a weapon, it's my life. Now let's start with this part of the session. Here we will try to cover these five topics. We will start with weapon accuracy with the help of circular error probable. Then we will see the statistics of accuracy behind a weapon, then terminal ballistics. After that, we will see the case study of Shahid 136 drones, in which is used nowadays very much in the Iran war. And then we will conclude this session with a quiz. So first of all, why do we need CEP, which is circular error probable? Suppose there are two identical missiles and two identical launchers, and we launch them from the same position, but there is there is a probability that both of them will land in different position, in slightly different positions. It is due to several external factors such as drag force, Coriolis effects, and other factors which Shirish has explained. So, CEP is a radius of a circle centered on the target in which 50% of the shots land. If a weapon has small CEP, it is said to be very accurate. For example, a precision missile, which has a CEP less than 1 meter. If a weapon has a medium CEP, it is said to have a moderate accuracy. So its CEP can be around 50 meters, and its example is guided artillery. If a weapon has a relatively large CEP, it is said to have low accuracy. For example, the atomic bombs that were launched by USA towards Hiroshima and Nagasaki had a very large CEP because we did not need precision there, as the whole region was the target. So, to compute the radius of the CEP, we will now understand about standard deviation and bell curve. This is important to compute what exactly is the radius of the CEP. What exactly is CEP? The value of CEP. So standard deviation measures how spread out values are from average mean in a data set. So simply let's take an example of five people. Let us take two cases. In the first case, the heights of the people are very close together. The values of their heights are very close together, and if we see them in real life, we might not be able to differentiate between their heights. In the first case, we say that we have small standard deviation. Here, the mean is 170 centimeter. Similarly, in the second case, as you can observe, the mean is 170 centimeters here also. But if we observe these five people in real life, we might be easily able to differentiate between who is taller and who is shorter and who does not have, who is in the medium height. So the values are relatively more spread out, and it is said to have a relatively larger standard deviation. Just for your information, the formula of standard deviation is summation of x. X is each element in the data set minus mu, which is the mean of the data set. We square it and take a under root of it, then divided by n, which is the number of elements in a particular data set. Now let us understand what a bell curve is first. Bell curve is a pattern that we see throughout statistics. It is used also used to find the CEP. Here our main idea is to find the area within under the curve. If we observe between plus minus 1 sigma, which is one standard deviation, the area which is covered it is covering is 68%, which means if the radius of a circle, uh, taking a target as a center, 68% of the missiles will land in that particular circle. Similarly, the area covered by plus minus 2 sigma is 95%. So now we need to compute which what value of standard deviation, what value of constant multiplied by standard deviation is having 50% of area under the curve to find the CEP, the radius. So from the bell curve, we observe that around 0.85 sigma, 50% of area is being covered in the bell curve. So if we see CEP is being defined as 0.85 multiplied by sigma, which means at a radius of 0.85 sigma, taking the target as the center, 50% of the missiles would be landed there. If if we take an example of a drone or a missile having a standard deviation 12 meters, we can see that its CEP is 10 meters. So around, we can say that in around 10 meters of radius from the target, 50% of the shots will land. Now let us try to work an example with an example of the Shahid drones, which are famous in the current Iran war. Uh, Disclaimer, these values are not exactly accurate. We have used this to simplify our calculations. Okay, so it is given that there is a sigma, the standard deviation of 11.77 meters. It is because of a GPS error, which we will talk about in our further slides. So first of all, we calculated the CEP, which is 10 meters here. And then we can say that the probability of hit within 10 meters is around 50%. If we compute the same for the radius of 20 meters, the hit will come out to be 80%. So to conclude, almost half of the Shahid drones will land within 10 meters of the exact GPS coordinate. Exact GPS coordinate. So through this, we can calculate the probability of hit we observe through the bell curve, which comes out to be 1 minus e raised to minus 1 by 2, which is minus 0.5 into r square divided by sigma square, where sigma is the standard deviation. This we have calculated through the bell curve. Now let us move to the next slide. In this, the first formula, if we replace sigma with CEP, we also get the value of probability of hit as 1 minus e exponent. Exponent is 10 raised to minus 0.72 multiplied by r divided by CEP the whole square. Now let us view the probability of multiple shots. So the probability of hit with n shots is equal to 1 minus a bracket 1 minus 1 p single raised to whole n. Here p single is equal to the p hit. So the probability of hitting a shot with a single drone is p single, and the probability of missing is 1 minus p single. For n shots, it would be 1 minus p single raised to n. And then the probability of hit within 8 shots, n shots, is 1 minus this term. So we computed that for a single drone to hit a 20-meter range, here we have taken a 20-meter building, we computed in this example, it came out to be 80%. For two drones, when we plug in this value in the P hit with n shots, we get 96%. Similarly, for three drones, we will get 99.2%. So that means if we launch three of these similar drones towards a building, towards a 20-meter building, it is almost certain that it will hit that building regardless of the drag force and other external factors. Now let us see missiles versus target sites. We have done it for several other distances as well. For a 5-meter car, the probability comes out to be 28 meters. For a 10-meter range, which is the CEP radius in this case, which we had computed here, comes out to be 50%. In a 20-meter building, which we can see in this case is 80%. And for a 50 meters facility, it could be a factory or a nuclear site or an army base, it is around 98%. Now let us see how GPS guidance work. We are seeing these examples from the point of view of the attacker. During this situation, there are 2 points of views which we will be observing. First is the attacker, which is trying to inflict damage, and second is the defender, which is trying to save its region. So first, let's see how does GPS guidance works. It is found in most of the drones and the missiles these days to prevent high CAP. So let us see the guidance loop. How exactly does this GPS works? First of all, the weapon receives a GPS signal and it computes its position, its exact position. Then it compares its actual position with the optimum path, also known as the target waypoint, from which we take the lowest time, or the path which is the safest for the missile without getting intercepted by interceptors, which we will see later in the slides. Then it calculates how much it has been deviated from the path with the help of delta x coordinate, y coordinate, and z coordinates. To calculate these, we need at least 4 satellites. 3 satellites are for x, y, and z coordinates, whereas the fourth satellite is to calculate the exact time after launch. First of all, let us see the trilateration formula before going further into the guidance loops. The trilateration formula is D is equal to C into delta T, where D is the distance to the satellite from the weapon to the satellite, C is the speed of light, delta T is the time taken for the signal to travel between satellite and the weapon. Okay, after that, we move on to the fourth step. It adjusts its control services to go move towards the optimum path from which it has been deviated, and it repeats this these 4 steps 10 times per second throughout the flight to remain in a certain position. Now let us go towards the defender side. The defenders would try to jam or spoof these GPS to the GPS to prevent the missiles to attack their region, to protect their economy, their people, their army bases, etc. For this, to prevent this, the attackers have some backup. In case of Shahid drones, we use INS backups. These are known as inertial navigation systems. Here we calculate the exact position of the weapon of the drone with the help of this given formula, where x, which is the position of the drone, is equal to x naught, the current position before the GPS was jammed or spoofed, plus v naught, which was the velocity before it was jammed or spoofed, into the time, plus half into a. A is the acceleration, which is calculated by the accelerometers and the gyroscopes, which are present inside of the drone, multiplied by the t square, through which we get the drift as only 1 kilometer per hour. Now we will be seeing more about the perspective of the defender side through jamming and spoofing. So to prevent GPS jamming, GPS tracking, we apply jamming or spoofing. Jamming means that we flood the GPS frequency with noise because GPS is essentially a signal, as we have seen in the first step, which is basically to receive the GPS signal. We bombard the satellite with uh, noise. So the reason behind this is when the signal to noise ratio drops within a certain threshold, the receiver is no longer able to receive the satellite signal, thus it is lost. Here the signal to noise ratio, also known as SNR, is equal to P signal divided by P noise. And as we discussed, if the SNR is less than the threshold, the weapon gets lost. And the CEP grows from 10 meters, as we have computed earlier, to hundreds of meters. So it also depletes the accuracy by over 100 times. Now let us see another example, another way of preventing GPS tracking, which is also known as spoofing. Here we directly attack the GPS of the drone. In jamming, we were attacking the satellites. Uh, so here we bombard the GPS, we bombard fake GPS signal to override the real ones, due to which the weapon becomes essentially confused and it is diverted off course. It was used by Iran to capture US RQ-170 drone in 2011, which was landed intact. And for your information, this drone was actually the inspiration for Shahid drones, which now Iran is using against the USA. Now, to prevent the jamming and spoofing of these weapons, which could result to a huge loss to the attacker country, they have taken, we can take around four countermeasures. So first is INS backup, which we talked about in the previous slide. Second is the multi-constellation GPS. It uses US GPS, Russian GLONASS, EU Galileo. It is very hard to jam all of them simultaneously. The third way is low altitude flight. So essentially, we fly our weapon in low altitude region and use terrain as the shield for jamming and spoofing. It reduces effectiveness of these two processes. The last one is terrain following algorithms. We use camera or radar data and compare it with preloaded terrain maps for backup navigation. Now let us see what happens when we hit the target. Now, what happens when we hit the target? The maths behind it is known as terminal ballistics. It is the math of impact. It's uh, so it is essentially the transfer of energy into destruction, as we know that energy can neither be created nor be destroyed. Here we here we use mainly three types of energy. First is kinetic energy, which is half mv square, where m is mass and velocity, v is velocity at impact in meter per second. So if we double this velocity, we will be increasing the energy by 4 times. Second is impulse and momentum. Um, Impulse is essentially how force is transferred to the target at a small duration of a time. It is being defined by F into T, where F is the force, T is the time duration, is equal to M, which is the mass of the whole weapon, into delta V, which is the change in velocity. But the most significant type of energy we use here is the blast radius. Here E is the explosive energy released. It is the most amount of energy that is released during the time of impact. It follows a cube root law, which means that R is directly proportional to the one third of the root of energy. So if we increase the energy by 8 times, the radius would be doubled. Let's take another example of with the help of Shahid 136 drones. Another disclaimer, we have used these values for simple calculations. If we take the mass of drone plus the mass of warhead, warhead is essentially the part of the weapon which carries the explosives, and it is used during the moment of impact. Here, the mass, the total mass has been given as 200 kgs. The speed at impact is around 51.4 meters per second, and the explosive mass un- inside the warhead is around 40 kgs of RDX. RDX is an explosive here. The energy density of RDX, which we already know, is around 5.36 megajoules, which is 10 raised to 6 joules per kg. So first of all, we calculate the kinetic energy, which we get it as 264 kilojoules. Then we calculate the blast energy, which is essentially the multiplication between warhead and explosive mass and RDX energy density, which we get as 214 megajoules. To understand this value, it is around 1,000 times more than the kinetic energy. Through the blast energy, we calculate the blast radius, which we get it as between 18 to 25 radius meters of blast radius. We get the total energy as 2,14,264 kilojoules when we combine kinetic energy and blast energy, also known as chemical energy. So what does a 25 meters of blast radius means? Between 0 to 5 meters of the blast, it is known as the lethal zone, which means there is a complete structural collapse and fatality is near certain over this region. In the radius of 5 to 15 meters, there is severe damage. Walls are destroyed, and casualties happen here usually due to the blast and the debris. Between 15 to 25 meters, there is moderate damage. Windows and doors are destroyed, and the injuries are from secondary fragmentation. And at a radius greater than 25 meters, there is light damage. Usually, glass breakage and a psychological effect on the personnel. Now let's move ahead. As we have discussed in Shahid drones, we usually use blast or high explosive type of warhead. But there are other three approaches to for these warheads. Okay, so the we have discussed this before. So now we'll move on to fragmentation. So essentially, in fragmentation, the warhead breaks into high velocity sharpener with velocity as high as 200 to 1500 meters per second. The velocity we can calculate here by under root 2 E by m. E is the energy at blast and m is the mass, the total mass. It is effective against personnel and light vehicles. We are going to discuss shape charges in the next slide. But before that, let us discuss penetrator or bunker busters. So usually, as you may have observed, Most of the important resources a country hides, like nuclear facilities, it is inside a bunker. And most of the important army personnel and important people in the country also hide within a bunker during war times. So for this situation, there is another type of warhead known as the bunker buster. Here, the kinetic energy of the bunker buster is given by half mv square, which you already know, and it has a very high velocity. It is made up of hard steel and tungsten rod to deliver all the kinetic energy at a single point. It penetrates the reinforced concrete before first, and then it detonates inside, destroying everything inside the bunker. Now let us move to shape charges. The shape charges was first inspired by the Monroe effect, which was discovered in 1888. A hollow or lined cavity in an explosive focuses energy into a narrow, high velocity jet, which dramatically increases the penetrating power against the armor. Here, the copper inside the hollow lined cavity becomes liquefied and then it penetrates the steel armor. So, this is the math behind the penetration. Here, P is the depth of the penetration as given below, L is the jet length of the jet multiplied by the root of density of the copper jet divided by the density of the steel armor. This formula we can compute easily. Now let us move ahead. Let us see the example of Shahid 136 drones. These drones are currently being used in Iran-Israel conflict. It has also been used in Russia-Ukraine conflict. It has a wingspan of around 2.5 meters. Its warhead is around contains around 30 to 50 kgs of RDX. It has a range of around 2000 kilometers with a speed of 185 kilometers per hour, and it uses its guidance, which is GPS plus INS, which we have talked about in the earlier slides. This is a relatively cheaper drone having a cost of 20,000 to $50,000. During war times, $50,000 is not a lot because countries tend to spend more than this, more than 100 times of this for a single missile. So now let us see GPS guidance and CEP of Shahid 136 drones. We have computed before the CEP of Shahid drone is around 10 meters. So which means around 50% of the strikes of the Shahid drones land within the 10 meters of the target. The GPS correction removes most of the drag and wind error. So even a $50,000 drone achieve a near precision accuracy, which is cheap in wartime scenario, where protection is the first priority and attacking is also the first priority. So how does this guidance work? So pre-launch, the exact location is uploaded inside the inside the drone. These GPS receivers listen to the satellite signal and compute the real-time position as we have discussed in the previous slides. Then the INS backup arrives if the GPS is jammed or spoofed by the defender country. It continuously corrects its error and continuously adjusts its position. After it reaches the desired area, it does a terminal dive into the target at high speed for maximum kinetic energy transfer, and then it explodes its warhead. Okay, Now let's move to the next slide. So, in the current Iran conflict, we have observed that multiple of these drones have been launched. It is due to the simple probability that it is due to the simple fact that the probability of hitting increases when we launch multiple such weapons at the same time. So, the probability of at least one hit is equal to 1 minus p raised to n, where p is the probability which that each drone gets through the interceptor, which we are going to talk about in the upcoming slides. So the probability of not getting through for one such weapon is 1 minus p. Then the probability of n weapons not getting through is 1 minus p raised to n, and the probability of at least one hit is 1 minus this term. Here n is the number of drones which we have launched. Let us see through the example of the conflict during April 13, 2024. Here, Iran had launched at 170 Shahid drones at Israel. All were intercepted, but at a probability of 30%. There was a probability that at least 30% of the drones could get through. So through the above formula, we can compute that the expected hits was almost 51. Okay, now let us see what advantage this gave to the attacker country. In this case, it was Iran. So interceptor missiles are mostly very expensive because interceptor does not contains missile. It is a whole system. So it was around $3 to $12 million it took to for each defensive intercept. And sometimes these interceptors were missing their targets. So for some drones, it was also taking multiple interceptors, which increased the cost significantly. And as we have discussed, the Shahid drones are comparatively very cheap in price at around $50,000. So we get the cost ratio at around 100 times, through which we get to know that these weapons and mathematics can also be used to hamper the economy of the country before sending the real threat. Now let us see the interception mathematics. Let us go towards the defender side that day, which was Israel. It uses Iron Dome, which is a very famous interception system. It is a state of the art interception system which is said to be the best, one of the best in the world, and it has been tested many times throughout history. Now, let us see what kind of mathematics it uses. First of all, the system contains four things: launcher, control system, radar system, and then let's see the calculation. The time. First of all, it calculates the time, which is d, the distance between the launcher and the threat, divided by the velocity of the interceptor minus the velocity of the threat. So it calculates the time which is taken to reach. It is exactly the relative velocity between the interceptor and the threat. Now then we calculate the position of the threat with the help of x x threat, which is the current position of the missile, plus v threat, which is the current velocity of the weapon multiplied by the current time t. All of this is computed within 1 second, and it only goes in highly populated areas to protect their civilians and their economic structures, to preserve these interceptor stockpiles as they are very expensive. The cost of the missile interceptor itself was around $50,000. It is one of the interceptors used by Israel, also known as Tamir interceptor. It has a success rate of 90%. Now let us see the numbers during the conflict in April 13, 2024. Iran had launched almost 170 Shahid drones at Israel. So Iran was the attacker country here. These missiles are also known as kamikaze missiles as they are used for decoy to deplete the resources of the defender country. And then the 120 ballistic missiles were also launched, which were actually the real threat. It had a 99% interception rate, but it was due to the combined efforts of Israel, US, Jordan, and Saudi Arabia. Jordan and Saudi Arabia geographically are almost in between Iran and Israel. And to defend, it took more than $1 billion to defend uh, those particular regions. Now let us see the evolution of the strategies throughout the years. The CEP of the weapons have been improved by 99.9% in over 80 years. It was so now let us see the history of it. In 1944, the unguided bombs used in World War II had a CEP of around 1000 meters, which meant it required hundreds of bombers to guarantee one hit on a factory. And those times, factories were essentially used to gather resources for a country. So those were one of the first facilities to be attacked. Then in 1972, during the Vietnam War, uh, the USA had used laser guided bombs. It had a reduced CEP of around 10 meters. And during the 1991 Gulf War, the GPS guided JDAM had a CEP of almost 5 to 10 meters. And at in 2000s, the cruise missiles had a reduced CEP of 5 meters, which had which was done by the missile Tomahawk. For your information, Tomahawk was the missile that was used uh, in killing of the children in Iran in the current war by America, or Israel. We don't know. Now, during 2020s, first of all, these four missiles were the state of the art missiles during these times. But in the present time, even low cost GPS drone have near precision of around 10 meters, like we have seen with Shahid drones. Let's move further. Now let us move to the perspective of the defender country, how they will try to defend their region from these drones, because drones have become the mm, major strategy for warfare, and it is quite a problematic strategy that directly attacks the economy of a country. The following are four. These are the four solutions that people came up to counter these strategies. First is missile interception. It is presently the most effective strategy, having a 95% success rate. But as we have seen in the previous slide, the cost disadvantage is huge, and due to which these interception missiles have a limited stockpile. The other solution to this drone strategies is cannon. We use cannons which have 10 to $50 which cost per round, and its hitting probability is equal to the burst length multiplied by the hit probability per round. But the problem is that it is effective at only a short range, less than 3 kilometers. Thirdly, we can use electronic warfare, also known as jamming or spoofing. We have also seen this in the previous slides. It is cheap, but it does not directly attack the physically attacks the drone, and it was defeated by several backups. In the case of Shahid, it was defeated by the INS backups. This is the major problem of electronic warfare. And the last one, according to me, directed energy laser. It is going to be the future of counter drone strategies. This is currently limited by technology, weather, and range. It has a cost as low as $1 to shoot when it is operational. Uh, its P is equal to E divided by T, where E is the energy to destroy the target. Let's move ahead. Now let us see the comparison of the weapon accuracy table of several weapons. As we have discussed, Shahid is a kamikaze drone. It uses a guidance which is GPS plus INS and has a CEP of around 10 meters. It can hit a building. M982 Excalibur is a type of artillery shell which has been discussed quite in detail by Shirish. It uses a guidance GPS plus IMU. It has a CEP of around 5 meters and it can hit a vehicle. The Tomahawk cruise missile, which we have discussed earlier, is a cruise missile, and it has a guidance of GPS and TERCOM. It has a CEP of around 5 to 10 meters, and it can hit a window comfortably. And these are other missiles, and the last one is the World War II gravity bomb, as we have discussed earlier. The it This was the exact bomb which was carrying the uh, bomb atomic bomb thrown by the USA, launched by the USA towards Japan in Hiroshima and Nagasaki, was a free fall bomb. It had no guidance, and its CEP was fairly larger at around 1,000 meters. It could hit a city block. Now, here are some key formulas for your quick reference, which we have talked about in the latter part of this session. The formula of CEP we discussed, which is 0.85 into sigma. Then we discussed the probability of hit of a single shot. Then we discussed the probability behind swan strategy. Then we discussed the GPS distance, and then the kinetic energy, and then the blast radius. After this, let us try to summarize this half of the session. So, mathematics in weapons has been used in these areas of mathematics have been used behind weapons. First is differential equation, which has been talked about by Shirish in detail. Second is statistics probability, which is CEP, swarm probability, and normal distribution of errors. We also talked about Newtonian mechanics, such as kinetic energy, impulse, etc. Then we talked about the trigonometry behind these weapons. For example, the trilateration from satellites. We discussed several numerical methods, and then we also saw the cost behind the warfare. And to summarize this session, let us conclude the session by summarizing it. After that, we will take a quiz for which the link would be sent by Shirish. We first started with flight. We discussed projectile motion and drag. We saw atmosphere, the effect of atmosphere such as wind, Coriolis force. We saw propulsion. We saw interior ballistics inside of propulsion. We also saw the accuracy, which was the CEP and the statistics. And after that, we saw the impact, maths behind the impact. with the help of kinetic energy and blast radius. So, to conclude, here is the conclusion of the summary of Shahid 136 drone. And to conclude this session, I would like to say that mathematics is not just behind the weapon, it is the weapon. Okay, Shirish, can you send the link?
Yeah. The link has been shared in the chat. I request everyone to join and participate in the quiz. Has everyone joined the link? I will be starting the quiz in 2 minutes. I hope everyone has joined. Now I am starting the quiz. Everyone be ready. So the quiz will end in next 2 minutes. So I hope everyone has completed the quiz. Here's the leaderboard, the top 5 students. Congratulations to them. I'm now ending the quiz. David, DJ, and 24 BDS. Congratulations for achieving the podium.
Okay, guys, thank you for being such a lovely audience. I hope you guys enjoyed today's event. I'll just post the Google form for attendance in the chat. You can fill it and then leave. Thank you.